Welcome to ECE 442-542. On the screen you will see something that's probably going to be there most of the semester, which is a list of announcements and a list of goals prior to starting the class. You've maybe checked the D2L website, but most of the material that we will be communicating with this session or this semester will be coming to you through D2L, especially if you're in the online section. But there's a PR unit already there, and that stands for Prerequisites and Review. If you want prerequisites or review material on Laplace, block diagrams, state space, Bode, and MATLAB, it's there for you to look at. There's a Unit 0, which is dealing with preliminaries, and that contains some links to an overview of control. If this is your first control class, you might want to read a little bit about that just to give you a background on what it is that control does or what it is historically. We will sort of be jumping in and just start assuming we know certain things about maybe why we want to do what we're doing in this class. In Unit 0, you will also find a passport assignment, and that's due in a little bit, a few days. What's today, the 11th? So that's due in 12 days. You have quite a bit of time, but the reason I'm giving you so much time maybe is because I'm changing it up from previous semesters. If you've taken classes with me, now what I want to do is when I look at your face, I want to see one of your favorite foods. That's the way that I will now start to connect with you as an individual. Don't take that wrong, and maybe that's the wrong thing since this is right at a food hour, meaning maybe I will be hungry during this class, but hopefully we'll get through it. But your name, and if you want to be called something other than your given name, that's what is referred to by the nickname. And hopefully you will give me something that I can actually use in class, and an email, and a photograph that needs to be up to date. And as I said before, the unique feature that's going to connect me with you is your favorite food. And in response to listing that food item, I would like for you to tell me why that's your favorite food and when you like to consume that. Maybe it's best in the morning, maybe it's best at late night, I don't know. And the ingredients. Maybe it's something I haven't ever heard of, so you need to give me the ingredients so that I know what it is that you are referring to when you tell me this is your favorite food. There is then one more set of questions under item 4 before your signature on number 5, and if you submit this into the Dropbox on D2L, then that counts as your signature. You don't have to worry necessarily about signing the document. But the fourth point or item has 4 different questions I would like you to answer after maybe looking at some of this dealing with Bloom's taxonomy in item B. And I won't go into that. I will let you look at that on your own. And homework 1 is already posted. If you want to get a fast start, it's not due for a while, but you'll have some time to pursue that. And a lot of that is actually material you can maybe do now based on your prerequisite knowledge. Some of that anyway, and some will have to be delayed until we get to that content at the appropriate time this semester. We talked before we came on air about the attachments, and we've just discussed the passport. Let's talk just briefly about the syllabus, and maybe what you want to know here concerns the room, which has been changed several times, and I think we're approaching maybe a steady state, but who knows, maybe we will change again. So stay tuned. We have a week between our next visit. It may change a lot between now and then. We don't have class next Monday. I think you probably all are aware of that. I didn't know how many people to expect today, thinking you might take advantage of that time frame, but maybe you have other classes besides this one. Office hours are staggered, but they are on Monday, Wednesdays, and Fridays. Monday is sort of before this class from 4 to 5. Wednesdays are from 12:30 to 2:30, and Friday from 10:30 to 11:30. And I'm not sure when we will have homeworks due, but they will be due. Obviously, the one is due on the 30th, and I think that's a Monday. So just pay attention. I might vary the date with which those are due. I don't think I will plan on those being due on Friday, since D2L a lot of times is being updated right at midnight, which is when I usually like to have you submitting your assignments. That's when the Dropbox will close, is at 11:59. There really is no one assigned text. Actually, all of these you should be able to, all of the texts that are listed you have access to without making a purchase, and the others are sort of reference books. If you want to go find an old edition somewhere, you can probably buy one if you like to have a hard copy or something very durable in your hands while you're reading. The other thing that you might be concerned about or interested in would be the exams, and I think these dates are what we are trying to work towards. March 8th is the Wednesday prior to spring break, so that you don't have to necessarily study all during spring break, but you can. That's fine. You'll have another test and you'll have a final. The final is on a Thursday. That's the last day of finals. But it is earlier in the day, so make note that if you are just working on Mondays and Wednesdays, or if you've scheduled to be here Mondays and Wednesdays, think ahead for Thursday, May 11th. It's at 1 to 3, which is a different time for the final exam. The others are, I think, all on Wednesdays, the 8th of February, etc., and the April 12th. I will let you look at the outline, and now I gave away the final exam in the previous semester on the syllabus. Now I'm giving you the final exam for this class, but maybe I haven't narrowed it down quite as fine as I did in a previous class. Yes? The final is mandatory, and it's not extra credit. So the final, if you were looking, did it say extra credit? It said 30%. Pardon? Yeah, 30% is not extra credit. No, I'm sorry if that now, but you can probably drop the class without my signature, I think, if that's desired. Other questions on the class and its structure. So here we may not have 24 questions, and some of these line items actually have multiple parts. That means there's maybe 30 of those. Maybe I will have 30 questions, since it's 30% of your grade on the final. But pardon? True false. Yeah, if you get one of the 30 true false wrong, you've got them all wrong. How's that? No. Yes, I've heard of people saying if you can get them all wrong, you'll get 100%. Good luck with that. All right. Now what I want to do is get into a quick overview about why you might want to study digital control, and then we'll get into system modeling, unless there are questions about the process of the class or the way it's set up. But this is how it will work. or function. Why digital control? And now we get to start drawing. Maybe. Our system and here we sometimes refer to that as a plant. That's not something that's green and has leaves, but it could, I guess. But our plant usually is some dynamical system. And we describe it. You've already, hopefully, the prerequisite for this is 320A. Hopefully you've had transfer functions in 320A. And you could think of, oh, a circuit that has a transfer function. That's my plant. That's G of S. Maybe you're not happy with that, but now it's giving you an output, Y of S, and in an analog version of this class, you would have a controller that's being used to hopefully help you achieve some desired performance behavior. Maybe it's tracking that reference signal, maybe it's responding to disturbances, maybe G of S is varying and you want to make the closed loop system look about the same, even though G might look quite different between different realizations of that particular system. But this is now a conventional analog control system. And that's what we have studied. And here is a signal that we've identified in earlier classes as the error signal, the difference between the reference and the output. What we may want to get around, or what D of S, this analog controller, might be susceptible to now, is what I want to list, and that's now trying to motivate why we might study this class, which is digital control. D of S may be susceptible to several things. One is environmental conditions. Temperature or moisture or humidity. The components in that D of S, which could represent a PID controller or a phase lead controller if you've had control, but those components might age. And you've probably had to spec resistors before, and now you know that they have tolerances associated with those, and maybe you don't want to deal with those tolerance issues in D of S. Noise could be getting into the analog system, and the parameters that make that up, the R's, the L's, the C's that are in that D of S, may drift or be expensive. Or unreliable. D of S, the analog version, may not give us as much flexibility as we would like. And what does that maybe mean? Well, a digital device, which is what we will focus on in this class, a digital device might allow more flexibility, meaning we could potentially introduce some control logic, some if-then-else statements, for example, which aren't doable in an analog controller. We might want to make some changes without soldering or resoldering or desoldering. We may want to do updates. Introduce a completely new control strategy. We can then just burn that into the control or the digital device, and now we have a completely new controller. That's what this class is trying to or is worried about, and that is to replace this analog controller, D of S, which is some digital device. And that could be a microprocessor, a microcontroller, a computer, a DSP, everyone's favorite, an FPGA from an earlier class, but that could then be used to realize these controllers. And what we want to do now is simply show how we can extract or remove that analog controller and replace it with a digital device. And the block diagram is going to look fairly similar. Here's our system with the output. The input to the system is still going to be analog because our system is analog, but now if we want to have a digital device, now we're dealing not with S's, but now we're dealing with Z's, a Z transform, and we now have a transfer function that's D sub D of Z, and coming out of that is just some string of numbers or sequence of numbers, and that's not going to be a valid way to drive the system, G of S. So we have to convert those digital numbers into analog numbers, and that's our D to A converter. Coming out of the D sub D, we have to now have a D to A converter. Here is our controller. This we could think of as the discrete or the frequency domain version of the analog input, which is now we're calling U of Z. But if we have the original system, what we're driving that system with might still be an analog reference input, R of S, and we can't or we won't be applying that directly to our digital device, which is this D sub D, and now we have to take this original air signal and put it through a analog to digital or an A to D converter to drive or then to have the signal coming into the digital controller. Maybe didn't give myself enough space, but here is our original air signal, but this signal now is the frequency domain version of the sampled air signal, and we'll call that, or we could call that, E of Z. This is what we now want to replace our original analog system with, is this configuration of an A to D, a digital controller, and a D to A to replace our D of S. And obviously we need some clock signal that will allow that system to function properly. And this system now in contrast to an analog control system, we are now sampling this air signal and then using that to drive our controlled system. So this is now called a sampled data system. What we are going to be focusing on is figuring out how to create that d sub d of z. Meaning, do we now convert g of s into a discrete system, or do we worry about controlling or finding a d of s and then discretizing that, or finding a discrete equivalent for d of s and calling that the d sub d of z? So we have different ways of going about designing these controllers. This is a sampled data system. We could have what I will refer to as more of a pure digital system. So we now might start with a system, not g of s, but a g of z, a system that's beginning as a digital system. Now we're looking, if we do this in the frequency domain, all of our signals are now the z transform of the output, the z transform of our reference signal. And let me just call this something a little bit different. Let's say that's d sub d bar. Since our system is digital, we don't need to really worry about converting signals from analog to digital or vice versa. Where this g of z is inherently a discrete time system, which gives us then this pure digital system. Either way, we are going to be trying to find these controllers d sub d of z, or I may just say d of z. In order to do that, we need to figure out how do we come up with this capital G of z, or how do we deal with g of s and relate that to a d sub d of z, for example. We need to figure out how do we model these systems, and that's what we'll talk about next. Meaning, I'm sure that you all really enjoyed modeling or analyzing circuits in ECE 320. That's one way of coming up with a system. And what we need to do is figure out how to deal with either analog systems in the time domain and the frequency domain, and discrete time systems in the time domain and the frequency domain. But here, we're going to assume that we're dealing with linear systems or linear models. We'll concentrate on linear models. In the analog, we can have a time domain or a frequency domain depending on what we are given or how we want to work with that. In the time domain, that might mean that we're dealing with differential equations. And we could get state space representations for these time domain equations. If it's a differential equation, suppose it's now y double prime of t plus 4y prime plus 13y of t equaling u of t, where conventionally y of t is our output and u of t is our input. You didn't see anything, did you? I have no idea what I just did. But then we can go into the frequency domain. Or transfer function description. And can you see that by just looking at the differential equation? Can you find now a g of s which you can think of as the ratio of the output's Laplace transform over the input's Laplace transform? And what does that transfer function look like? So we have 1 in the numerator. What's the order of our system? Second order. So we have an s squared in the denominator, and that's going to come about if we Laplace transform the second derivative. In the denominator, we then have s squared plus 4s plus 13, and that's now our system described by a transfer function. And that's maybe where we start. Maybe we're given that g of s. And now we have to decide, how do we sample the system? What's our sample period? And then how do we design a controller to modify or change that dynamic behavior? That's in the continuous time setting. If we went digitally, and I'm assuming this is, you're comfortable with that at this point, and if you're not, you have a week to get comfortable. That's the next time we visit each other. The digital, I'm anticipating where we're headed, but it gives you a feel for what this looks like compared to the analog case. In the time domain, again, we could have this in the form of a state space representation. For discrete time systems, we don't have differential equations, we have difference equations, where we now could say, oh, we have y at the n plus 2 sample period plus, or minus, let's say for this example, minus 0.4 y of n plus 1 plus 0.4 y of n equaling u of n. Again, the terminology, typically we use y's to be our output, u's will be the inputs, and we can now go into the frequency domain like we did in the continuous time case. We will learn how to do z-transforms, how to convert a difference equation into a transfer function by going through the z-transform of that difference equation. If you're given a signal, can you, or any waveform, can you find the z-transform of that? And that's a part of this class. We'll worry about z-transforms, regions of convergence, etc. So now the question was, is this difference equation equivalent to the second order differential equation in the time domain? It can be a sampled version. This is not a sampled version of the previous that I remember. I don't think I discretized this differential equation, but we will show how to convert these derivatives into differences, which now allow us to take these differential equations into a linear difference equation. And when you ask a question, please, if I don't repeat it, remind me to repeat it so that the people online go, I have no idea what he's talking about. They may do that even without me answering a question, huh? Hopefully not too many times. But this, we will learn how to go from a differential equation into a difference equation, how to go from a transfer function g of s into a transfer function g of z. And that will then allow us to become more comfortable designing these controllers for the discrete time system. In this case, I'm simply showing or illustrating what you might be worrying about. But here we have two delays between y of n and the higher advanced version of the output. So this is a second order linear difference equation, like we had a second order differential equation because of the two derivatives. And in this case then, we would have a 1 in the numerator. We would have a z squared. This z squared is an operator, like s is an operator, or you can view it that way, but z now is a complex number, just like s is a complex number. But z actually will be an advance, and z to the minus 1 will be a unit delay. Meaning, and we'll get to that, maybe I'm getting ahead of myself, but if you're familiar with block diagrams that are based on integrators in the time domain in the continuous time setting, now we'll start talking about block diagrams that are made up of delay blocks. And that's a little bit easier. Now you just have to sit there and wait one delay and then pop out the other side of that delay block. So these unit delays are maybe easier to think about than these integrals that you're used to thinking about for block diagrams. But now we have this interconnected system of unit delay blocks with gains, delays, and summers, and you just are having to sit there and wait until the next time instant, and then you pop out the other side of that delay block. So it's a unit delay. In this case, we will be becoming comfortable drawing block diagrams, all delay block diagrams associated with linear difference equations. And in this case, you would be expecting two delay blocks. And we'll then interconnect that so that if we push something into the input, or if we wiggle u of n, we need to wiggle things and not jump on things. And then that will trigger the output response y of n as it moves through this all delay block. Here, the z squared is associated with that unit or that advance of two time steps. Then we have a minus 0.4z. Maybe I shouldn't have done it this way. Maybe I'll change it. Why don't I do, well, no, I don't want to change it. Yes, I do. I'm talking to myself. I apologize, but it's late in the day. And I haven't had anything to, never mind. So let's say that's a 0.1. So now we have a plus 0.1 on that side so that you know where that, well, I guess I had a plus sign and a minus sign. Maybe you could see where those were coming from, but now it's a little bit cleaner. And we now have a second order system in the frequency domain. And what we will start to become comfortable with is those poles are just like poles in the continuous time case or the analog case. They govern the dynamic behavior of your system. Except now stability in a discrete time system is something a little bit different than in the continuous time or the S-plane. In the S-plane, where was our system stable, or where did we want our poles for our system to be stable? in the left half plane. And that you should remember from 320, I hope. I think, did you talk about stability? Maybe, maybe not. But now we're collapsing this infinitely expansive left half plane down to a disk of finite area, which is the unit disk. And now we want our poles to live inside this unit disk or unit circle for our system to be stable in the discrete time setting. Meaning if somebody now, even after one lecture of this class, if they said, is this system stable? You could plug that polynomial into your calculator or the quadratic formula, since it's second order, find the roots, find the magnitudes of those roots, and as long as their magnitude is less than 1, you can say, that system is stable. So now you can go home and check the stability of all of these second order transfer functions. You can pass them around to your friends. Now after class you'll definitely have napkins and you'll be able to write it on the napkin. You'll pass him down and you'll say, hey, what's the stability of this? I don't know, I'm enjoying my favorite food, but let me figure out which of these systems is or is not stable. But what we want to be able to do by partway through this class is be comfortable moving back and forth between these different representations. Or we need to learn how to convert between the different model representations. Now I saw everyone light up when I said 320. You have fond memories of 320. Yes. Let's go back then in time and let's analyze a circuit so that we can feel a little bit more comfortable with where this model might come from or how we might find a G of S. Oh, I just lost half the class. If you're playing along online, I guess you've already turned down the YouTube video and left and decided to go get a taste of your favorite food, since I mentioned 320, but hopefully not. Let's look at a continuous time model, and this should be a review. There's a RC circuit from, let's say, a 320 class. What's the order of that circuit or system? How many energy storage devices do you have? You have 2 capacitors. So it's a second order system. You should be thinking, if I find a transfer function, it better have a denominator, unless I have pole zero cancellations, it better have a denominator that's second order. If I'm finding the differential equations that govern the behavior of this circuit, I'll find either one second order differential equation or I'll find 2 coupled first order differential equations. How do I write my equations that govern this system's behavior? I think I know how you're going to want to solve this, but humor me. How would you solve this? Transform it into the frequency domain. Yep, we like the frequency domain, don't we? What if we don't do that? Let's stay in the time domain. We'll just, since this is a new year, let's start out on a, that was probably one of your New Year's resolutions. You wanted to solve this circuit in the time domain. Right? No. Your New Year's resolutions weren't that exhaustive? I remember one of mine was, I think, that very thing. All right, so let's do it in the time domain. Let's now, what do we want to concentrate on in terms of variables that might be helpful in describing this circuit's behavior? What do we focus on? You told me it's second order, and how did you determine that? Because of the energy storage devices, your capacitors. So maybe it's some variable associated with the capacitors. And now Eli and ICE help us determine which variable is the important variable if we're dealing with capacitors. Eli's for inductors, and ICE is for capacitors. And which variable is differentiated in ICE? ICE was telling us I is equal to C dV dt. The variable that's being differentiated is the voltage. That's maybe the one we want to focus on when we have capacitors. With that, let's now say, let's call this x1 of t. And the variable associated with capacitor 2, let's call that x sub 2 of t. And let's try to write our equations in terms of x1, x2, and their derivatives. And just for the fun of it, since we already have an input, and that u of t is not the unit step, although you might be from 320 thinking, oh, u of t, that was always the unit step. Now it's just a generic input. U of t could be any waveform we want. It might be an exponential, it might be an exponentially damped sinusoid, it might be a sinusoid, or a combination of sinusoids. It could be a unit step, but it's just our input u of t. Let's call the output. So we now have an input u of t, that's the voltage source. And let's say our output is the voltage dropped across that second capacitor, x sub 2 of t. And we now want to find some differential equations that govern the behavior between the input u and the output y. And if you were to do this in the frequency domain, what would you probably be doing? Sleeping? It's not quite that late, but I could probably take a nap. You guys can carry on. Let's do KCL instead of KVL. And I may get a little squirrely because it is late at night or late in the day, and I haven't had enough in my system. So I hope you're okay to tolerate me if I start laying down or jumping or shaking or something. Let's do KCL. Suppose we now call this node 1, and let's call this node 2. And I'll try to color code these. So that if we have KCL applied to node 1, we're interested in what? With KCL, we know that the sum of the currents entering, or the algebraic sum of the currents at a node equals 0. Suppose we have all of these going out of node 1, those currents need to sum to 0. Or if we now look at the KCL equations for node number 1, in terms of x1, x2, and u, what's the current going to the left out of node 1 in the horizontal direction? The voltage dropped across R1 is simply x1 minus u, and the current is going to be that voltage divided by R sub 1. This current then, let me quit labeling it. That current is now simply x1 of t minus u of t over r1. What's the current going through C sub 1? No hints allowed. Right? We can use ice, so that now we wanted to write it in terms of the voltage, x sub 1, and we could now say that that's plus C1 x1 prime of t. And that's the current going down in terms of x1, x2, and u, going down through capacitor C sub 1. What's the current going to the right out of node 1 in terms of x1, x2, and u? We've drawn the current going to the right, so we want to write these equations as if the leftmost node of R sub 2 is the higher potential. So let's now say that's x1 minus x sub 2 divided by R sub 2 for that current going to the right out of node number 1. And that's now all three currents going out of node 1, and we said those three, since they're all leaving, had to sum to 0. That's now one equation. It has a first-order derivative of x1. That's fine, and we'll be able to solve for that and actually get one state equation from that one equation. What about node number 2? This is the U of A, so we do things in red and blue. But node 2 is color-coded in... Is there a game tonight? No, tomorrow. Oh, yeah, tomorrow is our game. So node 2. Now going to, let's say we want currents going out of node 2. We could say we want a current going to the left and a current going down. And we do the same thinking that we had before, except now it's relative to node 2, so that the red current going to the left is x sub 2 minus x sub 1, and divide that by R sub 2. And what's the current going down through capacitor C sub 2? That's now ice in terms of C sub 2 and x sub 2, so that we now have C sub 2, x sub 2 prime. And so there's another first-order differential equation in terms of x sub 2, x1, and x2. It's x sub 2 prime. We have an x sub 2 prime and an x sub 1 prime. We now have two coupled first-order differential equations. There's our second-order system. What's the output equation for this system? What is y of t in terms of a linear combination of the input u and the variables, the state variables, x sub 1 and x sub 2? It's pretty easy, isn't it? Y is just x sub 2. Maybe it's too easy, and that makes it hard. But in this case, the output equation is simply y of t is equal to x sub 2. They're exactly the same thing. Those are our governing differential equations. If we want to now write that in state space form, we simply need to find an x1 prime equation. We have it. We need an x sub 2 prime equation. We have it. We just need to isolate x1 prime and x2 prime on the left-hand side and solve for equations including just x1, x2, and u, and none of their derivatives on the right-hand side. Let's now find, via some algebra, a state space representation? Show of hands, how many did this in 320, a state space representation? I probably didn't expect to see too many hands. I don't know that we did it. We being when I taught it a year or two ago, whenever I taught it. It's been too long ago. But you can figure this out. We now want to find an x1 prime equation. We go up to our node 1 Kcl equation and simply put x1 prime, or try to isolate that on one side, so divide everything by c sub 1. Then we have an x1 prime sitting on the left, and if we add and subtract appropriately, everything else will move to the right. If we do that, we'll have an x1 prime is equal to some combination of x1, which includes r1 and r2 and a division by c1. Do you see that, maybe? And putting those over to the other side. So now I have this. I have that term, I have that term, and they're going to be divided by c1. Or I now have a minus, since they're going on the other side. I have a 1 over r1 plus a 1 over r sub 2. They are all divided by this c sub 1, and that's scaling x1 of t. Then I have an x sub 2 term. That's what I've highlighted in blue, and if I add that to both sides, I'm adding plus x sub 2 over r2c1 to put it onto the other side, or it will end up on the other side. What did I just say? R sub 2. And I also have a u term, or an input term. And if I add that to both sides, this is on the same line, but I'm running out of space, plus 1 over r1c1 u of t. Questions on that? And if you don't see that right away, go home and write it on your napkin, and you'll soon figure it out. But you're just performing algebra to find or solve for x1 prime. That's why you did algebra when you did it, when you did that in second grade or third grade, whenever you did algebra. Maybe not with state space representation, but we're big boys and girls now, so we need to start doing state space representation. What about x2 prime? This one's maybe easier. We don't have as many terms, but let's now divide everything by c sub 2 and isolate x2 prime on the left, and we now have x2 prime is equal to 1 over r sub 2 c sub 2 x1 of t minus 1 over r sub 2 c sub 2 x sub 2 of t. And do we have an input in that second equation, a u of t? No, so we don't have any direct connection driving that time rate of change of our second variable. And what is that? That's the time rate of change of our capacitor voltage, C sub 2. And that's what this state space representation is telling us. It's telling us how those voltages are changing on the first capacitor and the second capacitor as we have them as a function of R1, R2, and C1 and C2 and the input U. And our output is just x sub 2 of t. Well, that was fun. So let's go a little more fun. Let's do a block diagram. So fun, we now, well, never mind. So let's do a block diagram. This is in the time domain, and it's a continuous time. And we can find this all integrator block diagram directly from our state space representation. What was our system order? Or how many state equations did we have? We had 2, didn't we? So we're looking at having 2 integrators in this block diagram. And did anyone get an analog computer over break? That's what we're building now. We're building an analog computer, which is just based on integrators, summing junctions, and gain blocks with some signals. Suppose that I say, let me inject into this rightmost integrator x sub 2 prime. What happens when I integrate x sub 2 prime? This is hard math. We simply get x sub 2. And let me now put the other derivative into the leftmost integral, so that now coming out of that integrator is x1 of t. And what we want to do now is interconnect this so that x sub 2 prime actually is created from this combination of r's and c's with x1 and x sub 2. Meaning, x sub 2 prime is made up of 2 different terms. X sub 2 prime now is going to be the sum of 2 different terms. It's going to be x sub 2 scaled by a minus 1 over r sub 2 c sub 2 there's x sub 2. That's one of my inputs that makes up the output, or x sub 2 prime, from that summing junction. The other piece, the other signal that comes in to create x sub 2 prime is this first term on the right-hand side, and that's a scaled version of x sub 1. And we already have x sub 1 identified in our block diagram. We simply need to scale it by 1 over r sub 2 c sub 2 and allow that to go in and produce x sub 2 prime. How do we create x1 prime? Well, it's similar. It's just now, how many terms are we going to have coming in to build x1 prime? 3. We have 3 terms on the right. 1 is an easy one. That's the weighted version of the input u. And that weighting is 1 over r1 c1. And there's u of t. I won't widen my, oh, I do have a wider paper. That really bothers some people when I start making my napkin bigger than theirs, but deal with it. That was one of your New Year's resolutions, right? I'll tolerate Tharp's cutting his napkin and making it wider or longer. So there's what happened to u. The input u. Most of you left a long time now. Stay with me. Stay with me. So there's one of our 3 signals making up x1 prime. Another one is going to be created out of a scaled version of x1, and that scaling was this minus 1 over c1 with this boy. My sketching didn't get any better over break, did it? You don't have to answer that. So there's the other second signal. And what's our third signal? It now needs to be weighting x sub 2, which is the 1 over r sub 2 c1. Those three signals now combine to create, if this is now our all integrator block diagram, we can inject any input we want, u, as long as we know what the r's and the c's are, and we have these integrators, and out pops x sub 2 and x sub 1. Our output was actually x sub 2, which says then that we could call this signal y of t. Meaning, if you wanted to solve that coupled set of differential equations, you could build this analog computer, inject the input u, and out pops your solution, x1 of t and x sub 2 of t, because you've interconnected it appropriately. What if somebody wanted that in the frequency domain? This is the time domain. Those are integrators. What's an operator version of an integrator in the frequency domain? 1 over s. So now if we want to take this into the frequency domain, I'm getting lazy, so I'm going to call these, or relabel these gains. What if I call this alpha 2-1, alpha 2-2, alpha 1-1, alpha 1-2, and this let me call beta. So that was in the time domain. What if we go into the frequency domain? The structure is exactly the same, except now those integrators become 1 over s's, operators, but it's interconnected the same as before. Here we have an alpha 2-1, there was our alpha 2-2. This is now y of s, or x sub 2 of s. We have an alpha 1-1, and I'm including the minus sign in those coefficients. We had our beta here. And we have one more coefficient, this alpha 1-2. From that. And this particular signal is x1 of s. There's a frequency domain block diagram description of that same RC circuit, second order. Oh, we're not done yet. We're having so much fun. Let's take this one more step. Let's put this now into a state space representation. We haven't done that yet, have we? Well, sort of. We just didn't put it into matrices. There's our state space representation. We can now put that into a matrix representation. But now I'm going to collapse those coefficients into the alphas that I've created. I had a second order equation. I have two state variables. I'll stack those on top of each other. I have an x sub 1 and an x sub 2. Here's my alpha 1-1. Here's my alpha 1-2, my alpha 2-1, and my alpha sub 2-2. times the state. Then I have something U. What's the input matrix look like? Did U influence x sub 2 prime? Was there any U term in x sub 2 prime? No. So that's going to be a 0 in the second row of that input matrix. But up here, we did have a feed or a signal from the input feeding in to create x1 prime. In a state space representation, this is actually our A matrix or the system matrix. This is our input matrix B. And now if we want our output equation, we now need to find matrices such that when they're multiplied by this state vector and this input signal, we get a scalar output y of t. What's the dimension of the matrix that needs to multiply our state vector? How many outputs do we have? 1. So it needs to be 1 row tall, and it needs to be 2 columns wide to be compatible with our state vector x sub 1, x sub 2. And it was simply pulling off x sub 2, so our output matrix C is going to be the row vector 0, 1. And what's our output matrix dimension? I'm sorry, what's the direct feed-through matrix? The matrix connecting our input to the output. How many rows does it need to have? Needs to have 1 row to be compatible with the 1 output that we have. And how many columns does it need? 1. And what's in that direct feed-through matrix D? 0. We're not done, are we? Because we're trying to chase our tail. We now have a state space representation. Let's go back into the frequency domain. Find it. Yes, let's go back into the frequency. Let's find a transfer function in terms of these 4 different matrices. So I won't put in numerical values for R's and C's. I won't force you to invert a matrix explicitly, but you can do it virtually with symbols. Meaning this is our cheer from last semester, is it not? Do I have to get my pom-poms out and start cheering? Yes, yes. Okay, I brought them with me. No. But how do we take this state space representation and get it into the transfer function? We could go back to the block diagram and find it from the block diagram, our transfer function. Let's find it algebraically, but let's just remind ourselves that we could find from the block diagram, but let's find it from these equations. We have an x prime is equal to a x of t plus a b u of t and the output equation is cx plus du. To take a time domain equation into the frequency domain, we need the Laplace transform. And we can do that even with matrices. What happens when we Laplace transform a derivative? Do you remember? Multiply by s. So now we have s capital X of s. And in general, we would need to subtract off the initial condition of that state vector, minus x of 0 minus. Since we're dealing with the transfer function, we're going to neglect initial conditions, but let's just put it in there for completeness. What happens when we Laplace transform ax of t? A is a constant matrix, so the Laplace operator can slide right through that, or the A can be factored out of the Laplace, and now we're just Laplace transforming x of t, which is just capital X of s. So that we now have A, capital X of s. Bu is similar. The B is constant, and we Laplace transform little u of t into capital U of s. Since we're playing or looking for the transfer function, we can neglect that. And we want to combine these common terms, which means that I want to now place a placeholder in there, an identity matrix, so that I can now say that I have Si minus A times capital X of S is equal to Bu of S. And I said we wouldn't have to compute this numerically, but we could do it virtually or with our equations. Or let's now invert that matrix Si minus A to solve for or to isolate capital X of S. And now we could do all of this in the frequency domain, and we could inverse Laplace transform the right-hand side to obtain x sub 1 of t and x sub 2 of t, which are stacked in this vector form in the frequency domain. But if we want the output equation, or the output in terms of the input, which is what we want for our transfer function, we can now Laplace transform this constant output equation to find y of s is equal to c capital X of s plus d u of s. And let's now use this capital X of s in there, so that we can end up with y of s is equal to c times si minus a inverse b u of s plus d u of s. That u of s is in common, which allows us to factor it out on the right-hand side. And we've now gone full circle, or we've actually been able to catch our tail, and we now have an expression for our transfer function, capital G of S, in terms of our state space representation, which was in terms of these matrices, A, B, C, and D. And that's our cheer. We have our cheer, one of those, I think. Did you forget that over the long break? That break wasn't that long. It's now C times the quantity Si minus A inverse B plus D. And that's now, we'll find something very similar when we start doing Z transforms of difference equations. And we'll find a capital G of Z expression or a transfer function. But you have a whole week to get back up to speed on this material. There's a PR section, a unit, which is prerequisites and review on D2L, and I will see you in a week.